Work in progress.
All right. Anybody have any questions about anything before we get started? I put an announcement on Canvas last night. I'm going to have, in addition to my other regular office hours on Tuesday and Friday, I'm also going to be on Zoom tonight between 7:30 and 9. I'll send out a reminder later this afternoon, but if there's anything you want to talk about, and really anything, but especially with respect to the test on Wednesday, yeah, call in and we'll talk. All right, one more example for the product rule here. So I have this function h, which is cobbled together as the product of x and some other function g of h. And I want to find h prime of 3. So what should we do first? I want to find h prime of 3. What must I have in order to get there? What's that? I actually don't need g of x based on what I have, because I want h prime of 3. I know what g of 3 and g prime of 3 are, so I don't really need to know how g is defined. You have an idea? Sure. Specifically in, well, let's say this. Let's say h of x is equal to f of x, g of x. Then what is the product rule? Let's just remind ourselves. Plus f prime g. So if I want to apply that to my function here, what is the derivative of the function I have here, this x times g of x? I guess in this case, we can say that f of x equals x. So then f times g would just be, or sorry, f times g prime would be x, g prime of x. What would f prime of x be? Just 1, so I'll just 1 times g of x. Quick rewrite. So any questions about how we got here so far? And then if I want to find h prime of 3, I can just plug in the individual pieces. So what's the value of x here? How about g prime of x? 2. And then g of x? So h prime of 3 should equal 11. Also 10? Okay, scared me. We're good. It happens. Any questions on this one? Go ahead. Two like component functions. G of x, I have no idea what it looks like, but it doesn't really matter. F of x, I know f of x is equal to x in that case. Anything else? All right. Sure. How did I get 1? I'll put it to the rest of the room. How did I get 1 there? Right. So yeah, that's the derivative of f. So yeah, power rule on just x is just, it'll be 1. Anything else? All right, quotient rule. So I'm going to develop this one. You know, all derivatives come from the same place. So we're going to start there. The limit as h approaches 0 of f of x over g of x. Oh, nope. Let's start with the capital H. And while I'm doing this, I want to revisit a question that I got a lot last time. So think back to the product rule. Product rule is when I have two functions multiplied together. Does it matter in that case which one I call f, which one I call g? No. When you're multiplying, the order is irrelevant. Which, so it makes sense that, the product rule is totally defined by multiplying functions together and then adding a sum of those two pairs. So multiplication and addition, order doesn't matter for those operations. So look at the quotient rule here. If I have one function divided by another, does it matter which function I call f and which function I call g? Absolutely. So those of you who've seen the quotient rule, you know that what the result here is going to be where order matters. And that's why. The function f over g is fundamentally different from g over f. So I have f of x plus h over g of x plus h minus f of x over g of x all over h. So you're going to see a lot of similarities between the way this one gets developed and the product rule. But before I go any further, I'm going to deal with I'm going to try to get a common denominator so I can simplify things a bit. So I'm going to multiply everything, both top and bottom, by g of x plus h, g of x. So this numerator becomes f of x plus h, g of x, minus g of x plus h, f of x, all over h, g of x plus h, g of x. We good so far? Common denominator manipulation. Now, just like last time, I'm going to introduce this mysterious middle term and then immediately remove it. Minus f of x g of x plus f of x g of x minus g of x plus h f of x all over h of g x plus h times g of x. Let me pause there for a bit. Any questions about what I've done so far? Just to kind of take some of the stress off you. If you don't know where I'm going here, that's totally fine. This is kind of there's a lot going on right now. But this is we're all doing this to build up some shortcut for the quotient rule we can use without ever having to use this difference quotient again. All right, so again, like last time, I'm going to break this into pieces. So I get the limit as h approaches 0 of, and because we've done something like this, I'm going to factor some things out. So the limit of g of x times f of x plus h minus f of x over h g of x plus h g of x. And then I might have to explain this because I'm going to do a few things at once, but I'm going to flip some terms around. So I'll do minus f of x times g of x plus h minus g of x Still with me? So just like last time, we're assuming that f and g are differentiable. You know, if their derivatives didn't exist, we couldn't do any of this stuff. So now we need to look at what happens, see if we can evaluate these limits. One thing I'm doing now is this. I know that I can pull out. I'm going to factor out this 1 over g of x plus, or actually I need to keep the limit with it. The limit as h approaches 0 of 1 over g of x plus h times g of x times these things. F of x plus h minus f of x over h and the g of x So I'm almost out of room, but I only got one more thing to write down. So now that I've kind of moved everything and factored out in convenient ways, do we see any limits here that look familiar? How about this f of x plus h minus f of x over h? What does that look like? If I take the limit as h approaches 0, what does that become? Not f of x, but something related to it. So this part right here is going to become f prime of x. And that is the definition of the derivative, right? That difference quotient, the limit as h approaches 0 of that difference quotient. G of x is just going to stay the same. And then over here, you're going to have f of x times g prime of x. So we're almost there. We got the numerator. The numerator is going to be f prime times g minus f times g prime. But now we got to figure out that denominator that I'll write this more carefully for you in the next slide. I just ran out of room here. Look at this very first set of terms. Numerator or the denominator is going to become simply this, g of x squared. So got a little sloppy. So that's where it comes from. We can just use it in this form now whenever we have a function that looks like this. I can. No, we didn't. So this is a proof of the quotient rule. We just derived the quotient. This doesn't technically have anything to do with the product rule. It looks similar. But let's talk about that. Why does it look so similar? Where did derivatives all come from? Like, how are they all defined? Comes from the difference quotient, right? So I mean, when you're building a differentiation rule, they come from the difference quotient, which is why you're going to see a lot of commonalities in how they're developed. All right, let's do some examples, and while I do, I'll try to write the quotient rule down or actually have room. So if capital H of x equals that, h prime of x is equal to f prime of x times g of x. minus f of x times g prime of x all over g of x squared. So we said before with the quotient rule, the order of division matters. So it makes sense that the quotient rule is full of instances where order matters. You have subtraction in the numerator, so it definitely makes a difference what you call f, what you call g. You're dividing by by the square of one of the functions, so you better have that defined correctly. All right, so now let's apply that to this thing. So this function here, x, that rational function, how can I find the derivative of that? What rule was that? Power rule is going to definitely be part of this, but let's just break this up into pieces. So dy dx, we know we want to take the derivative of what, the numerator or the denominator? The numerator first, right? So I'm just going to take this first one slowly. So that derivative times x cubed plus x minus x squared plus x minus 2 times x cubed plus 6 prime all over x cubed plus 6 prime, or no, squared. Just deleted my straight line, which is the only, So we're not done. Got to definitely do a bit of simplifying, but any questions on how we wound up here? Right, we heard a call for power rule. What's the derivative of the first term, or the first set of brackets I need to differentiate here? 2x plus 1. Leave x cubed plus 6 alone. Minus x squared plus x minus 2 times 3x squared all over x cubed plus 6 squared. See if there's any simplifying we can get out of here. 2x to the 4th plus x cubed plus 12x minus 3x to the 4th minus 3x cubed plus 6x squared. I'm not going to worry about extending this bracket. Just collect like terms and then we'll be done. All right. Oh, sorry. Any questions about this one here? Yeah, I mean, it's so the thing with quotient rule is the product rule. It's pretty easy when it's as simplified as you can make it. Really, for this, I probably could have stopped it earlier, but this is the derivative at every step of the way. I mean, especially from here forward. The derivative had been done. I found dy dx with that. But it's all a matter of how much you want to keep simplifying or how much I ask you to keep simplifying, things like that. Go ahead. Where is it? Oh, there's a 6 in here? Okay. And thankfully, it doesn't get canceled by anything, so I can just... Is that all? All right. Thank you. Any other questions, corrections? All right. Moving on. Let's find the equation of a tangent line. So I gave you the equation of a curve and a point on it. I want to find the equation of a tangent line. Where should we begin? If I am asking for the equation of a tangent line, what operation do I know I have to do? Not always the quotient rule, but really, if I use the quotient rule, what am I really doing to the function? Yeah, I definitely need a derivative, right? But yes, in this case, I do need the quotient rule. So dy dx is going to be equal to, and I'll let you, let's start populating this thing. So if we do the numerator first, what's that first term in the numerator going to look like? 1/2. Okay, where did this come from? Okay, I'll just make a note off to the side. Derivative of radical x is 1/2 squared x, which really does come from the power rule, but maybe you've done that enough times that you just remember it by now. And the next term is just simply 1 plus x squared minus radical x times 2x all over 1 plus x squared. So I believe that's a good derivative. Should we simplify a little more? I got to vote for yes. Anybody not want to? What's our goal right now? Yeah, I really what I want out of this derivative is just the slope, right? I might as well, let's just try to get it without having to simplify. I mean, if I asked you to do it, you could probably do it. You could definitely do it. Excuse me. But now I want to evaluate this derivative at x equals 1. That'll be 1/2 times 1 times 1 plus 1 minus 1 times 2 all over 1 plus 1 squared. I believe negative 1/4, but I have been wrong recently. I feel pretty good about that, but let's pause there for a second. Are we okay with how we got that slope at this point? All right, now I want to get the rest of this equation for a line. What information do I have so far? Well, I told you a y value. We just found an m value. Also gave you x. Use that to find b. I believe that is going to give me b equals 3/4. So any questions on how we applied the quotient rule, how we evaluated it, how we found that equation, anything at all? All right, moving on. All right, let's find this derivative. What should we do? There you go. So kind of set a trap for you. This is one of those cases where could you do the quotient rule? Absolutely could. But I think there's a better, more effective way to get at this. So simplifying. If I simplify, how can I rewrite this? So yeah, you don't really need to factor, but let's start here. I can rewrite this like this: 3x squared over x plus 2 radical x over x. You okay with that breakdown? The one on the left is a little easier to see. It just becomes 3x. What does that second term become? And just kind of based on some of the questions I've heard recently, not even recently, but kind of every time I go through things like this, lean on your exponent laws. I think if I were to write something like this, x to the 6th over x to the 5th, what would that be? Right, it's just you're subtracting exponents, right? So maybe another rewrite we could do is this, is just express all of these exponents, or yeah, express all of these variables as having exponents. So 2 minus 1 is easy. But now I can rewrite this next one as a couple different things, but I'm going to go with 2x to the negative 1 half. You've been using those exponent laws for so long. Don't forget that you can use them with roots, and the powers don't have to be integers. That's a word. So now that I have this simplified, can I find the derivative easily? Oh, what's the derivative of 3x? And how about the other term? Minus 1 over the square root of x to the 3rd. You agree with that? Let me see how we got from there to there. Because honestly, I'm having trouble. So let me just go ahead and break that one out. If we use the power rule on this, 2x to the negative 1 half, this is going to become negative x to the negative 3 halves, which, yep, I think I agree, is the same as negative 1 over x to the 3 halves, which is negative 1 over the square root of x cubed. So I feel good about that. And just to be clear, if we would have gone through the quotient rule here, which is what I was halfway expecting to do, we would have been fine. We would have gotten the same place. Question? None of these things are incorrect. All these things are equivalent. But yeah, because we didn't. Yeah, I think you meant quotient rule. We didn't do the quotient rule because I think we found a faster way to do this. Let's say you're working on this and you disagree. The quotient rule, you're really fast with it. You really like it a lot more. That's fine. There's no problem there. Like I said, we could have used the quotient rule here and wound up in the same place. Any other questions about this? And just to kind of generalize that point. I've thrown, and we've talked about a lot of differentiation rules in here in the last week and a half or so, and really there are some times where certain rules won't work as well as others. But I'm just giving you a toolbox basically. It's up to you to decide when to use them. And really for this example, we use power rule. We could have used quotient rule. I can see a way where I could set this up doing the product rule. It would be really silly to do that, but you could definitely do that too. All right. So finding the derivative of tangent x, something we've not done before, but with the tools we have, this is something we have access to. Why would I bring up this function tangent x when we're talking about the quotient rule? I think I heard something. Yeah, tangent of x is equal to sine of x over cosine of x. So really what I'm asking for is this derivative. And if we apply the quotient rule to this, what's that derivative end up looking like? So I'll take the derivative of sine in the first term, derivative of cosine in the next. And since they're relatively new, what's the derivative of sine? So this first term becomes cosine squared of x. What's the derivative of cosine? Negative sine. So negative sine times negative sine becomes positive sine squared of x all over cosine squared of x. Does that simplify at all? How so? Equals what? Yep, so Pythagorean identity. Sine squared of x plus cosine squared of x equals 1. So I get 1 over cosine squared of x, which is equal to, I can simplify one more time, or at least redefine, secant squared of x. Any questions I haven't got here? Derivative of tangent x is secant squared of x. All right, so now we have derivatives for the three primary trig functions. Now I'm going to give you the derivatives for reciprocal functions. So saw the first three, or saw the first two a while ago. We just did this first one, and what I'm going to encourage you to do, just to kind of get some practice with the quotient rule, try proving these with the quotient rule. Now we go on. Okay. All right, I can come back to this at the end of class, but let's finish up. So now that we have those new rules, or those new rules, let's go ahead and use them. So I want to find the derivative of this function, secant of x over 1 plus tangent of x. I'll let you all walk me through that. How do I find this derivative? What's that first term in the numerator going to look like? Oh, sorry, couldn't hear that. One. Let's keep it in secant and tangent as far as we can. So for this first term in the numerator, which do we need to take the derivative of? Secant or 1 plus tangent? Secant. What's that derivative? Secant x, tangent x. Secant x, tangent of x, times 1 plus tangent of x. So that's the first term. Minus what? Secant squared of x times all over 1 plus tangent of x squared. Question? Of 1 plus tangent x. Well, we just did the derivative of tangent x, right? So if you take these terms one at a time, anything else before we see if we can make a dent with by simplifying at all? So if we expand some things in the numerator, we get secant x tangent x plus secant x tangent squared x minus secant cubed x all over 1 plus tangent x. Y'all okay just leaving it the way it is? I think it would simplify if we brought in some of the Pythagorean identities, but I'd rather just focus on the derivative. Or just, yeah, so I expanded that. Those basically distributing secant x tangent x to 1 plus tangent x. Secant x tangent x tangent x. What else? All right. Same function. Now I want to know, where does that graph of f have a horizontal tangent? So let me just copy down the derivative again. Okay. So I want to know where this graph has a horizontal tangent. Where is any graph going to have? So if I know that the graph of that function has a horizontal tangent, what do I know about the graph? What can I look for in terms of the derivative? Switching directions. So yeah, the graph is switching directions. I heard something about the slope, but not the first part. Sorry. Positive to negative slope or negative to positive. So what's true of the derivative at that point where that change is happening? What's the derivative equal to? Equal to 0, right? So that's what we're looking for here. And this is kind of a nasty situation. I have this, this function here is equal to 0. Is there anything I can do to make this a little simpler for me? Go ahead. So that's part of it, right? One thing I'll say to get us a little closer is this right here is going to equal 0 when the numerator equals 0. So I can start by looking at this. Secant of x, tangent of x. Actually, and since it was brought up, I'm going to factor out a secant from everything. So one of these equations, yes, can be very simple. Secant of x equals 0. It'd be really nice to simplify this thing in the brackets, though. So one thing I'm going to do here is let's remind ourselves of the other Pythagorean identities. So here's the one that we all remember: sine squared of x plus cosine squared of x equals 1. I'm going to divide all these terms by cosine squared of x. And this gives us tangent squared of x plus 1 equals secant squared of x, which means tangent squared of x minus secant squared of x equals 1. So this does simplify for us in a really big way. Let's do that before we. I can also rewrite this derivative like this: secant of x times tangent of x plus 1 all over 1 plus tangent of x squared. So then in reality, what we're looking at is just this: secant of x over 1 plus tangent of x. I want to set that equal to 0. So really the only equation we have to solve to find where x, or to find their horizontal tangents, is secant of x is equal to 0. Yep, we agree with that. The secant cannot be equal to 0. Let's go a little, let's see why. What is secant equal to, just by definition? 1 over cosine of x is equal to 0. Is it possible to divide 1 by anything and get 0? Doesn't make any sense. So, didn't truly find any horizontal tangents for this function. But that is the process for how you look for them. It all comes down to where that, basically you got to find where that numerator is equal to 0. The only thing you really have to worry about is to make sure that those x values don't also make the denominator equal 0. In this case, we didn't find it in the check. Go ahead, question. Provided that the denominator is not also equal to 0. And why do I say that? Why does the denominator need to be anything but 0? So it's actually defined. So you have 0 divided by something non-zero. That's 0. Anything else here? All right, I think that was it. Yep, that's all for 2.4, and I think I only have a. I'm assuming since no one turned it in, y'all saw to know that the quiz is going to be due on Friday. This section 2.4, I think I'll make it due on Monday at midnight. Yeah, not today. Yeah, I'd really like y'all to focus on the things you already know about and most of the tests. So I'll put that out to Monday. Yeah, sorry. I'll be on Zoom tonight. Remind you of how to find my Zoom room, but yeah, that's in addition to my office hours that I already have on Tuesday. And if neither of those work for you,